Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we have Arun Suresh, who is a PhD student at the University of Missouri. We are happy to have him here today to tell us about the crystallographic phase retrieval problem. Take it away, Arun.
Oh, hello, everybody. And first of all, thank you so much for having me here and organizing this entire summer of graduate student speakers. This is a wonderful opportunity. And on that note, I'm here to talk about the generic crystallographic phase retrieval problem. This is based on joint work with Dr. Dan Edidin, who's also in the audience, who's my advisor at the University of Missouri. And this is based on our paper together, which is now present in the archive under the same title, Generic Crystallographic Phase Retrieval. All right, so where do we begin? Well, we begin in the beginning, right? So what is CPR? And this is not the medical kind, right? So people in this day and age, especially like to study proteins, and one of the ways to study proteins is to sort of crystallize them and then shoot X-rays at them, right? So you have this X-ray source and you're shooting X-ray beams at this crystal, right? And what these X-rays do is that they interact with the structure of the crystal itself and they diffract. So what you can now do is put a photographic plate behind the crystal and sort of capture this diffraction pattern. And this is typically something you would see, and I've sort of blown up that diagram here. Zoom is doing not a great job at preserving that clarity, but hopefully you can see that diffraction pattern over here. So you could sort of conveniently ignore that big circle that's coming really from that experimental setup over here. And this is really just the beam itself, right? But the thing that we're really interested in, the signal that we're going to be working with, are these dots. And what we're particularly focusing on are the placements of the dots and their intensities, right? So essentially what we want to do is we're going to take this diffraction pattern, we're going to look at it, and we're going to somehow do our sort of phase retrieval information theory magic, and we're going to turn that into the electron density of the protein that we're trying to study. So really our work is like right here on that arrow, going from that diffraction pattern to that electron density map. And then of course, there have been a lot of models developed to take that electron density map and turn it into a protein model. And typically the process doesn't stop here. So once you have a protein model, people do the process all over again to iteratively improve their model until some sort of convergence is observed, right? Now, the thing that takes us from this sort of experimental setup to our model space is the following observation, right? So we're trying to recover the electron density of the crystal, and the observation, and this is something people have studied in sort of experimental settings, that and they've noticed that the X-ray diffraction pattern that they observe is really nothing but, well, the magnitude of the Fourier transform of the electron density. What does that mean? Well, we don't know the electron density, so assume it's some kind of signal, take its Fourier transform, that's going to be a vector, take its coordinate-wise absolute values. So when I put absolute values anywhere on the stock, that means coordinate-wise absolute values for a vector. And then what you would get out of that entire process is the same thing as the diffraction pattern that you're observing, right? So that's what people have observed sort of experimentally, and there have been papers written on that subject. So this is what's going to take us to the model space. And just to sort of improve the relevance before we go there, X-ray crystallography has been the topic or it has influenced about 60 Nobel Prizes, typically in the medical sciences and chemistry, although the initial ones were in physics, right, when the theory was still under a lot of development and scrutiny. But so now we're going to go to sort of the model space, right? So really our goal is to recover a vector X in Kn, and K in this talk is predominantly going to be either R or C. C is not exactly going to be relevant to the physical applications of the project because really the signals that we're looking at are inherently real signals. We're going to sort of flatten this image, and then sort of you can take this image and put it into a 0 to 255 grayscale map, and now you have a real vector with actual entries in it, right? So the real vector is really the thing that we're most interested in, and that's what the central results of the paper are, but we do address the complex case as well in the same paper, right? And the goal of the paper is to really recover a signal from its power spectrum, which is just a fancy word of saying, take the Fourier transform of the signal, take its coordinate-wise absolute value. And since we're algebraic, well, at least Dr. Edidin and I are trying to do algebraic geometry, we like polynomials. And so we put that square there, which allows us to transition very smoothly into working with polynomials, right? So this F is the discrete Fourier transform. There you have it, that's that matrix. And this omega is the primitive nth root of unity. Okay, well, it turns out that you could study this problem, and people have thought about it a little bit. But if you take the set of all vectors that have the same power spectrum, turns out that set is too big. In other words, the crystallographic phase retrieval problem as it stands is ill-posed. So we have to introduce a prior. And one of the priors that people do introduce is sparsity. And this is a very natural prior to introduce, because studies have shown that the electron density that we're trying to recover is about really just 1% of the total signal that we're going to be considering. So this is very experimentally motivated. And I note here, it's sparse in the canonical sense, which is an odd thing to note. But then when you think about it, you realize that certain signals can be sparse with respect to the standard basis. But then I can think about signals that are sparse with respect to other bases, like, I don't know, wavelets. So I can get this sort of diffraction pattern, chuck it into a wavelet transform, and now I get, you know, sparsity in that sense. And maybe it's sparse with respect to some other weird basis that we'd have to learn by doing some kind of data science or something, right? So in order to tackle it all at the same time, we introduce this notion of a generic crystallographic phase retrieval problem, where it's the same problem as before, but now X is sparse with respect to a generic basis V, right? And to understand what the word generic really means is the simplest way to put it is I ask you to close your eyes and pick a random basis, and then the basis that you would pick would be a generic basis, right? It's just, I give you a possible continuum of bases, and then I ask you to close your eyes and pick one. The thing that you pick will be a generic basis, right? On a more technical level, what that would mean is that this V comes from a set of possible bases, and this possible set, this set of possible bases contains a Zariski open set, right? So that's the more technical way of understanding what generic means here, right? So, and sort of later in the talk, we'll sort of formalize what it means to be sparse with respect to a different basis, and sort of will, in the paper, we note what that Zariski open set really is. I'm not going to go into that in this talk, but, you know, more details will be provided, right? But before we move forward with it, with sort of solving and tackling the problem itself, I want to give a little bit more background. And to that end, a related problem that has been extensively studied in the literature is the so-called frame phase retrieval problem, where we're not trying to recover a signal from its power spectrum or its magnitude of the Fourier transform, but rather what we are given is this n element frame. And we're trying to obtain the signal from the magnitude squared of its inner product with these frame vectors. So I don't have an unknown, I have an unknown signal, I don't know what it is, but what I do know is its magnitude of its inner product with all these frame vectors, and I'm trying to recover X from it. An equivalent an equivalent characterization of this problem is basically to obtain a vector from its magnitude squared. Again, coordinate-wise magnitude squared, given that the vector that we're trying to recover is in an m-dimensional subspace of that space, of you know, the entire space, right? And it's maybe worth taking a moment to understand this equivalence, because it's going to play a special role a little bit later into the talk, right? So why are they equivalent? Well, I'm going to show you one direction, but the other direction works very similarly, right? So what I'm going to do is I'm going to arrange the frame vectors into an m by n matrix where these would form the columns. right? So I have n of these, right? Typically n is bigger than m, right? So I have an m by n matrix, and I'm going to construct, and I'm going to call this u, right? So this is my frame. And I'm going to construct this function LU that's going to go from Km to Kn, and it's going to take a vector x to its inner product with these alpha n's, right? And so you want to realize what we're really doing is LU of x is the same thing as U transpose x. That's another way of thinking about it, right? So I'm taking the inner product with these frame vectors, and since U is a frame, since I should really say alpha n is a frame, U is full rank, so dimension of LU of Km is really just m. So it is honest, the image is an honest to God m-dimensional subspace of Km. And now I'll just think about recover this vector from my observations, right? Square, right? The absolute value squared of this, right? And then sort of once you have this, since the alpha n's form a frame, you could recover s, right? So that's one of the characterizing properties of the frame. So the sort of having this is the same thing as having that, and then you can sort of go backwards using the same logic. Okay, and then sort of this construction is worth keeping in mind because we're going to get back to it in a second, or in a couple of slides at least. Okay, so what's the deal with the problem? When k equals c, things are very, very nice for CPR because it ends up reducing to FPR, and people have been studying FPR since the dinosaurs roamed the earth, right? It's been studied for a very, very long time. And the reason it ends up reducing to FPR is because the discrete Fourier transform is just a linear transform when you're working with the base field of C. In other words, multiplication by F is an automorphism of this n element frames of Cm. And so instead of studying CPR, I study FPR, and techniques have been developed to do that. So things are very, very nice when K is C. When K is R, however, not so much. And it's a bummer because this is the case that we're most interested in, because this is the one that really people in the real world care about, right? And you can sort of get a hint that things are complicated by noticing that the FPR ambiguity and the CPR ambiguity don't have the same dimension to begin with, right? So for example, this is basically the set of all vectors in Rn that will have the same sort of magnitude squared, right? And again, that's what people care about in FPR, right? So this is my FPR ambiguity. And the ambiguity itself is just plus minus 1 to the n, because each coordinate that we have in our vectors can differ by only a sign. On the other hand, people have studied CPR before, and this is the CPR ambiguity is much bigger, right? CPR ambiguity, and this is actually studied in one of Dr. Ediden's previous papers. The ambiguity itself is plus minus 1 SO2, and this exponent is a little ugly, but we'll see where this is coming from. So it's this thing, and so this is much bigger, right? It has a dimension about n/2, which is something we could check using some dimension theory. But ultimately, what we see is that the ambiguity group is this product of these planar rotation groups. And that's something we expect because really what the Fourier transform, when you interpret it in the real sense, is doing is it's really rotating these vectors and it's changing the phase. And you'll have a bunch of sines and cosines. So this is very much expected, and this is really what we see, right? So the CPR ambiguity is much bigger. But there is a silver lining. There is a good news, right? And the good news is that CPR can be reduced to something that is similar to FPR, but that's going to need a lot of reformulations and representation theory. Okay, so long story short, in the language of internet memes, over the complex numbers, everybody's happy, right? Because the CPR and FPR, they immediately identify each other and as such are able to be simplified rather immediately. When over the base field of R, they don't identify each other. So a lot of translations have to be done before we can convince that they are in fact the same entity. So more work needs to be done, right? So that's really the overall story. And that's the story behind the paper, if nothing else is sort of apparent. Okay, now we're going to sit down and we're going to actually study, like sort of formalize a lot of the things that I've been saying, and we're going to sort of study what techniques were employed in the paper to settle the problems of the problem of this GCPR, right? And in particular, in this slide, it says we're going to concretely define notion of what it means to be sparse with respect to a basis, and soon we're going to formally understand this notion of recovery. Okay, so given a basis V, V1 through Vn of Kn and X in Kn, we write the V expansion of X is basically just expanded with respect to the basis Vn. We say that the indices where this vector is non-zero, well, those indices will form the support. The support is just the n such that xn is non-zero. And we say that X is M sparse if that support has cardinality less than or equal to it, right? So there are at most M non-zero coordinates in the V expansion of X. And what I'm also going to do is I'm going to define the subspace LS of V, which is basically the span of VI for I in S. Right, so I have a certain support S, and then I'm going to say, oh, this is just the span of those VIs in the basis, right? Okay, now I know that X is M sparse if and only if X is in LS of V for some S with cardinality. So because that really says that the number of non-zero coordinates here are just M. So this equivalence is almost immediate, right? And so this is a nice way of understanding M sparsity with respect to basis by just defining these special subspaces. And now we're going to understand the notion of recovery, given that we now understand the notion of sparsity, right? So we say that a basis V satisfies the Fourier phase retrieval condition for M sparse vectors, which is a mouthful, so I don't want to say it again and again. So I'm going to call it SR, right? If the following two conditions hold, right? So SR1 and SR2, the S really stands for subspace, right? Okay, so for all S subset of 1 through N with size M, if Px equals Py, then X is equal to Ty, where T is some unimodular constant, depending on your field, right? So that's a nice, concise way of writing that, right? And SR2 says, for any distinct supports S1 and S2 with size M, the intersection of the power spectrum values is the power spectrum of the intersection, right? So really, to boil it down and put it in English, right? So SR1 really says any two signals with the same support can be distinguished, right? So I start with the same support, and if two signals have the same power spectrum, then I can distinguish them up to a unimodular constant. And then SR2 says any two M sparse signal can be distinguished. And this is a little bit cryptic, but really what this is saying is if I have X such that if I have X in LS1 of V and Y in LS2 of V, such that Px equals Py. So that's what it means for X and Y to be here. Well, that's telling me that if I look at the places where S1 and S2 differ, well, X and Y have zeros in their expansion there. That's what it means to be here, right? Because you just look at wherever those two supports differ, X and Y will take the value 0, because this is the same thing as being in that intersection, right? So technically, and then you would use SR1 to conclude that you can distinguish them fully. Okay, so hopefully that part is clear. Okay, but Zariski opens, right, are huge. So it suffices for me to recover only a generic M sparse vector instead of every M sparse vector. Like I said, because a generic vector would just mean there's a Zariski open set of them that you can sort of recover, and Zariski open sets are huge. They are dense in the Euclidean topology, right? So it suffices to only recover a generic M sparse vector, especially if it's going to make our bounds a lot better, right? So we say that a basis V satisfies a Fourier phase retrieval condition for generic vectors if the following two conditions hold, where it's the same SR conditions, but I've literally just imposed a generic condition on one of the two signals that we're caring about, right? So for a generic X, if the power spectrum is equal for some Y, then they have to be the same up to a unimodular constant. And here, for SR2, we don't say that it has to be exactly equal to the power spectrum of the intersection. What I say is, well, maybe there is some things that go, maybe there are some signals that do things that we don't want them to do, but they're all stuck in a proper real algebraic subset of this PLS1 of V, right? And again, thinking about the bad guys being inside a proper real algebraic subset of this thing tells me that it's the generic vectors coming from the first component. Okay, so that's the SRG conditions. So to, again, to paraphrase, for a generic X with a support S, SR1G tells me that I can sort of recover everything up to a unimodular constant as, you know, for generic X. And for a generic X with support S, SR2G is telling me that there's no Y with a different support that has the same power spectrum. Okay, so that's what SR1G and SR2G are. And here's a nice little table that sort of captures all the notation that I just threw at you. So if you see a 1, we're caring about the same support. And if you see a 2, we're thinking about potentially different supports for our vectors. And if you see a G at the end of the statement, we're thinking about generic recovery as opposed to universal recovery of signals. Okay, and you'll see that just, I mean, I'm doing the song and dance about this generic recovery, and in the next slide, I'm going to tell you why that's extremely important and why that's relevant, right? So we have theorem 3.1 and 3.2. These are our central theorems in our paper, right? So if I take a generic basis of Rn, and I'm telling you that condition SR1 holds if n is bigger than 4m minus 6, and SR2 holds if n is greater than 4m minus 4. So another way of sort of understanding it is universal recovery if sparsity is in the order of sort of n over 4, right? Which is m is less than n over 4. M is going to be my sparsity level, so I can get universal recovery in R if the sparsity level is about n over 4, right? But when I impose this generic recovery condition, I can sort of double the sparsity level. So generic recovery, maybe blue was not the best idea here, so maybe I'll write here generic recovery for a sparsity of n over 2, so I can double that, right, which is quite nice. So, and we have sort of analogous results for Cn, right, for the complex numbers where SR1 and SR2 hold if, again, the sparsity level is about n over 4, and the sparsity level for the generic recovery is about n over 2 again. And these numbers are assuming that n is even, and that's going to be a standing hypothesis for the rest of the talk, that n is even, and we produce sort of odd the results for odd n in the paper as well. I just didn't present it here to not clutter the slides. Okay, a couple of things to note: that theorem 3.21 is not new, right? So SR1 was shown to hold with a better bound with 4m minus 5 in one of Dr. Ediden's previous paper. And then SR2 was shown to hold in this paper called Sparse Phase Retrieval by Zhu and Wang in 2014, but they used very different techniques. So we do provide a proof for a different proof for 3.1 here. Oh wait, sorry, I was pointing to the wrong thing. The complex case is what's not new. The real case is all brand new. So this is all new. Sorry. Okay, so this was shown to hold with better bounds in Dr. Ediden's prior paper with 4m minus 5. And then Wu and Zhu and Wang, they showed this using different techniques, but we still provide a proof for that in our paper, albeit it's a different one. Okay, so those are the main results. So moving forward, how did we get those results, right? Okay, so the first main reduction that we do is the so-called FR reduction. What we do is we take two supports, S1 and S2, such that LS1 of V intersect LS2 of V is an S-dimensional linear subspace, right? And this gives us a lot of control over what we're going to be studying, either SR1 and SR2, because I can just let S be all of M, which will tell me that the supports basically agree everywhere. So these two would be the same matrix. So I will be studying SR1 if and only if S equals M, and then SR2 otherwise, right? Right, so this is a very nice trick to sort of collapse both problems into one setting, right? So what I'm going to do is I'm going to write this LS1 of V and LS2 of V as M by N matrices U and V with S overlapping rows, right? So essentially what that would look like is my U, I should probably define. So let's say my LS1 of V is going to be something like V1 to VS, VS plus 1 to VN, and then LS2 of V. Well, there are S overlapping rows, so this is V1 to VS, and then I don't know, WS plus 1 to WN, right? So if I do that, then I can write my sort of frame vectors as, so the VIs would be the rows, and I'm going to call the columns alpha I, right? And then my frame V is again, so the rows are going to be my basis vectors WI, and the columns are going to be my what I'm going to be thinking of as the frame vectors beta I, right? So that's the setup that I'm going to be working with. So, and then we're going to do the same trick as before, right? So we're going to construct this LU function, which is basically, again, LU of X. You want to think about it as U transpose X, and LV of X is V transpose X. Again, I need to put this pesky little bar just to sort of account for the case that this is indeed a transpose and not a conjugate transpose, right? So inner product has this star as opposed to a regular transpose in it. So I put a bar there, right? And I realize, obviously, that the image of LU is the subspace LS1 of V, and image of LV is LS2 of V, right? Just by construction. So it's the same old story from before. And here's the idea for the reduction, right? So instead of studying the power spectrum with X stuck in the subspace, I'll say X is in Km, and I'll study PLU of X and PLV of X instead of this guy, right? And the trick to do so is to literally just rewrite SR and SRG in terms of LU and LV, and now we're going to call them FR and FRG just to be sort of formal about it, right? And I've sort of included that here, but all I've really done is I've taken the four statements from before, and wherever I see an X, I've just replaced it with LU of something, and that something is coming from KM, right? That's the only difference, but everything else, the wordings are all the same, right? And then the underlying thing that we're trying to do has not changed. It's just the language has changed a little bit, right? And this is going to help us a little bit because this is, as you can imagine, the F stands for frame. So this is going to reduce to the frame phase retrieval case in the very next slide, actually. So, we realized when K is the complex number, so this is kind of the easy case, right? So when K is C, we notice that F is an invertible linear transform from Cn to Cn, and that's going to help us a lot. How is it going to help us a lot? I can, instead of studying recovering X from P of X, or P really LU of X, what I will do is I'll try to recover X from just the magnitude squared of LU prime. Well, U prime is given by UF. And how did I get here? Well, it's actually coming from the realization that this is a thing that I want to study. Well, what is that? Well, that's the same thing by definition it's this, but LU of X is, sorry, where's the eraser? There we go. Is U transpose X. This is something we realized. F is a symmetric matrix. So this is just, F is the same thing as F transpose. So this is UF transpose X. Well, that's U prime by definition. Oh, I'm leaving behind all the squares after telling you how important they are to me, right? And this is, and there's a transpose as well, right? So this is U prime transpose, and that's the same thing as LU prime of X squared, right? So instead of doing that, I can end up doing that. And now we are in FPR realm, and now people have developed machines before, and I can check the problem and my equations into that machine, and it's going to give me a bounce. So since that is a little anticlimactic for me to just move on after that, I'm going to give you an overview on how this machine works, right? So what I'm going to do is I'm going to first note that the thing that I like to study in FPR, this inner product squared, and this is where I can turn this absolute value into something that looks a lot like a polynomial, into this, right? So this is a realization, and you can sort of realize that this XX star here is a rank 1 matrix, right? So say we want to study, FR2, right? Without loss of generality. Like I said, if the overlap is all of it, then we're studying FR1. So without loss of generality, let's just study FR2. So we don't want two vectors to have same absolute value squared, right? So suppose they do. Okay, so we have this alpha n star, xx star alpha n is beta n star, y star, beta n, and these are rank 1 matrices. And so I can sort of reduce to, instead of studying things about signals, I can start studying things about rank 1 matrices. So I can sort of translate this problem where I'm solving equations of this kind, right? Beta n star B beta n, and this was first sort of, at least I first saw it in one of Dr. Nixon's paper called Saving Face from 2014 or something. But I don't know if things have been in play before that also, like if these ideas were around before that also. But so I'm going to start studying equations of this kind. And what I'm going to do is I'm going to create a so-called incidence relation with all the bad guys, right? So I'm going to sort of create this big set, which is going to be the set of all my frames and all my rank 1s that do bad things, right? And what are bad things? Well, these equalities hold, right? So I'm going to not write out all the equations, but I'm going to build this big monster of a set, and then I know it's huge, right? So this is my I. This is my incidence relation. And now what I'm going to do is I have two flavors of projection. I can project down to the frame space, right? So this is my UV space, and I can project down to the rank 1 space. Right, I should probably really just, now that I've given them names, this is my AB space, right? And sort of a lot of algebraic geometry has been done to some things called determinantal varieties, which is what this is. And so I really like studying things like rank 1s, right? I know what their dimensions are going to be. So what I can do is I can do some algebraic geometry using these projection and sort of fiber dimensions. I can sort of do some magic and use some theorems from algebraic geometry to figure out the dimension. So use, I should probably say, use to get dimension of I. And one thing you end up realizing once you do get that dimension is that that dimension gets really small. So this monster gets really, really small as n gets really, really large. And that kind of makes sense, right? So these are all polynomial equations. So if the space that you're embedding this into gets bigger and bigger and bigger, well, the polynomial relations themselves are going to get smaller and smaller, smaller part of that big space, right? So I reduce this in size, or this incidence reduces in size as n gets larger. And I want to enlarge n so much that this incidence relation, the place where all the bad guys live, well, that dimension gets smaller than the dimension of my UV space, right? If that happens, well, then I know that for a generic pair of frames, there should be no bad rank 1 matrices that's going to cause all these equalities to hold. And then I could sort of wind back the clock and do all the translation back to get my FR2 statement, right? So the FR2 statement is equivalent to really what comes out of this machine, and that n, that threshold n that I have to grow this incidence relation by, well, that's going to be my bound, and I've told you what that is in a couple of slides ago in the main results page, right? And that's basically how the machine works. And this helps us settle. Oh, hopefully the bottom is visible. It's not visible because of the panel here, but hopefully that's visible to everybody else. But anyway, that's how the machine works. And then we've settled the problem for the complex case. And here's a happy cat so that we can take a small break before we jump into the real case, which is the more relevant one, right? So here we are with the real case. We're going to set k equals r. And for historical reasons, we will start indexing our vectors at 0, and we'll sort of denote the nth coordinate of a vector by this square bracket. And this is really done to sort of be consistent with the literature that is existing in Fourier and a lot of numerical analysis and Fourier phase retrieval kind of papers in the past, where people do this, and lots of computer scientists like this notation as well. So we're going to just change our notation to be consistent with all that literature that already exists. Okay, and again, it's worth repeating that this is the more important case that's motivated by actual applications, right? And this case is not as straightforward as case when k was c, because f is not a real transformation. And in fact, even if you want to think about complex frame phase retrieval and sort of do some weird translation, this is highly structured, right? If you take a generic real frame and you attack it with you attach a discrete Fourier transform in it, it's still heavily structured because of all the relations that exist. So it's not even a generic complex frame. So any sort of generic arguments you have is out of the window, right? So what we're going to do is we're not going to study the power spectrum anymore. We're going to study a related object, right? We're going to study the periodic autocorrelation of a vector, which is defined to be this sum here. And a thing to note is that there's bar here if k is c, right? So if you were thinking about the general autocorrelation function over the complex numbers, you're going to have to conjugate that second term. But we're working over real numbers, so there's no need for conjugation, right? And why is it okay to replace the power spectrum with the autocorrelation? That's because you take that autocorrelation vector, you apply the DFT to it, well, that's the same thing as the power spectrum, right? So it captures the same information as PX, right? So if you're doing an experimental setup, you take your observation and hit it with F inverse, and now you have the autocorrelation, and you're trying to recover X from that. So great, so it is actually valid to do this. So what's the strategy? Well, wherever you see a P sub L of something, replace it with A sub L of something because they capture the same information. And since AX of L is the same thing as AX of N minus L, where you basically do N minus L here, and I should probably have mentioned, I'm sorry about this, the indices are taken modulo N, right? So basically if you go over N, you're back to 0. Right, so that allows us to realize that AX of L and AX of N minus L are the same because just these two things swap places. So you can view that autocorrelation function as a n over 2 plus 1 tuple of quadratic forms in n variables. The bummer is the equations are too complicated, right? Because you're going to have all sorts of variables in. So if you have n over 2 plus 1 variables and n variables in each of the n over 2 plus 1 equations, and it's really highly complicated for it to study, for us to study that. And in particular, if you're thinking about reduction to FPR, that's really not possible because the machine is not compatible with equations of this form, right? It really, the machine likes separation of variables where you have, you know, things like this. There's a star here. Otherwise, the multiplication is not defined, right? So it likes things like this, where each equation has its own thing going on, right? It has its own variable. Here, all variables interact with it in all sorts of ways, and we don't like that, right? The equations are too complicated. So what we do is we do some, we find a new way to represent this autocorrelation function in simpler terms. And that's where the representation theory comes from. What we're going to do is we're going to realize this autocorrelation function as the second moment of a dihedral group action on Rn, right? And I'm going to illustrate this reduction for complex signals. So for a second, I'm going to sort of cover my eyes and pretend we're in CN where things are nice, because it's easier to get the message across when we're working with complex signals. But all of this can be translated to real signals as well, right? So what I'm going to do is I'm going to let D2N act on Cn for the moment via the following relations, right? So rotation means it's a cyclic shift. So basically I have a vector, it just gets shifted down, and the last coordinate is going to go back to the top. The reflection is going to basically reflect the vector across. So if I have a vector, the 1 and the n-1 is going to get reflected, 2 and the n-2 is going to get reflected, so on and so forth. 0 retains a special spot, right? Because 0 will go to n-0, which is still 0. So 0 will be the same, and everything else gets reflected about the center, right? So that's the action. I'm going to define the so-called second moment as this sum, right? So basically, this is just a normalizing factor, and the thing that matters is that outer product. I'm going to let each group element act on my signal, and I'm going to take this outer product and I'm going to sum it all over together, and I'm going to normalize it by the size of the group, right? And that's my second moment. And the first proposition that we come across is that the second moment and the autocorrelation function, they capture the same information, right? And here is a proof by example. And note that this is not a valid proof technique. So this is just there for illustrative purposes. And for the same purpose, I'm going to also temporarily forego the assumption that n is even, because n equals 2 is too small and n equals 4 was too large. So 3 hit the sweet spot there. So n is 3, and my vector that I'm trying to recover is xyz transpose. And I've sort of gone ahead and computed the autocorrelation and the second moment for you. And as you can see, there's your autocorrelation equation, and literally every equation is either a duplicate or a conjugate of the autocorrelation equation. Like, so this one's grayed out because these two equations are conjugates of each other. This appears here. So it's always true that the first row of the second moment is going to be your autocorrelation function, right? So this appears here, and literally the other two rows are just conjugates or copies of the first row. And there's in fact, there should be a 2n here, but what you realize is when you do the computation, you get 2 copies of the same matrix. So the 2's actually cancel out. So this is the second moment. And as you can see, they capture the same information. So that's really nice. So I can understand the autocorrelation as the same thing as the second moment. Okay, great. So now what I'm going to do is I'm going to consider a change of basis for Cn, with my new basis being the Fourier basis. So I take my standard basis, I chuck it with the DFT, and now I get my new basis, and I write Z and Cn in terms of my Fourier basis, right? So this is a representation of Z in terms of the Fourier basis, and you can sort of reinterpret the dihedral action that we have here in terms of the Fourier basis as follows, right? So the rotation acts by multiplication by omega to the negative L, and reflection acts the same thing as before. It just reflects the vector across the middle. Okay. And the really, really nice thing here is that this dihedral action, it decomposes Cn into a sum of irreducible representations, right? So it starts with V0, V1, all the way to Vn over 2, where V0 and Vn over 2, they are one-dimensional representations spanned by V0 and Vn over 2. And everything else is a two-dimensional representation, and you have this sort of pairing thing that happens, right? So Vk gets paired up with Vn minus k, and So those guys are in the middle over here, right? And you might ask me, well, why couldn't I do this trick before when I was in the canonical basis? Well, this decomposition is not available under the canonical basis. For instance, well, if I take R and I try to rotate E1, I get E2. Well, that's not going to be, it's not in the span of E1, En minus 1. Right. So this decomposition is not available in the canonical basis, which is why we need to sort of change the basis into the Fourier basis to get this decomposition. And so here's an illustration that might also help understand that dihedral action is the same thing, right? So let's take my Z to be like VK, which is the kth row of the discrete Fourier transform, right? So this is 1 omega to the K, omega to the n minus 1k, right? So instead of having you buy my word for it, here's, well, an illustration, right? So if I rotate my Z here, well, what's going to happen, this last guy is going to go to the top. So that's omega to the n minus 1k, and then my 1, my omega k, and then omega to the n minus 2k. And then what I can now do is, well, factor out an omega to the negative k out. And the first term would be omega to the nk, and then omega to the k, and then omega to the n minus 1k. Well, that's just some integer power of omega, so that's just 1. So that's omega to the negative k times 1 omega to the k, omega to n minus 1k. That's omega to the negative k bk, right? So so sort of going back, the same D2N action sort of translates to multiplication by omega to the negative L in the Fourier basis. And you can sort of check that reflections work the way I told you they would work. I'm not going to do that because I have a few minutes left. So what's the punchline, right? Why did we do all this? Well, the punchline is that there exists a quadratic function BZ such that each component of BC is a positive definite quadratic form that involves at most 2 variables, and the autocorrelation of 2 vectors being the same thing is equivalent to the B function being the same thing after taking the Fourier transform of the vectors, right? Why is this good? Well, this tells you that I have the same number of equations. The number of equations did not change. It's still n over 2 plus 1, but each equation is less complicated. There's no interaction between variables, and then there are no n variables per equations. There's at most 2 variables per equation, and we will see soon that this does the separation thing that we want that frame phase retrieval machine to do, right? Or the frame phase retrieval machine prefers, right? And the equations are structured, allowing reduction to this FPR techniques. Okay, and what makes this lemma work? The short answer is that the second moment has a very nice diagonal expression on the Fourier basis, and Dr. Edidin wrote a paper in 2022 that explores this in depth. And the slightly long answer is basically the proof of that claim, where I take this vector in CM, and I'm going to write this in terms of its Fourier basis, but I'm going to sort of pair it up together, right? The way I want the irreps to pair together. So my V0 and Vn over 2 guys are by themselves, and then everything else is paired up with their complement, right? So Z1 and Zn minus 1 are paired up, Z2, Zn minus 2 are paired up, and so on and so forth. And I'm going to shortly call them F0, F1, Fn over 2. And in the same paper, Dr. Edidin shows that the second moment over each irrep is simply just given by these numbers, right? And you can see tensors are scary, but ultimately I want, whenever you see a tensor like this, I want to think of an n by n matrix with a 1 in the ith diagonal entry. So this would be the 0th diagonal entry. So that's what that is. And then this is a 1 in the n over 2, so it's somewhere in the middle. So something like that, right? So somewhere in the middle is this thing, that's that matrix. And identifying that and then noticing that the magnitude squared is really just Z1 squared plus Zn minus 1 squared in this case, and here it's just Z0 squared, here it's Zn by 2 squared. So it's these magnitudes that we are really interested in. So when you put them all together, we see that the second moment captures the same information as just these functions, right? And ultimately, so my this B function is just going to be just these magnitudes, right? Z0 squared, Z1 squared plus Zn minus 1 squared, and so on and so forth, right? And our discussion shows, well, the power spectrum being the same, it is equivalent to the autocorrelation being the same. Well, from my first proposition, that's the same thing as the second moments agreeing. Well, I just changed the basis into the Fourier basis. And now this lemma tells me that the Fourier basis, under the Fourier basis, the second moment on this B function capture the same information. So having the autocorrelation agree is the same thing as taking the Fourier transform of my signal and having the B functions agree, right? And so I can do my final touches, where if I take a frame, I could do the same sort of trick as before, right? I take this inner product with alpha k, well, I can write it as this, and that lets me write each of the B coordinates as equations of this kind. And again, XX transpose, I want to think of that as a rank 1 matrix, right? And you can see the sort of separation of variables that we like, almost separation of variables. So here the variables are separated. Here they interact with each other a little bit, but they live in their own little islands, right? But still, this is good enough for the machine because I can tweak the machine a little bit to work with these kind of equations, right? So they are ready to be adapted into the FBR machine. So I can mimic the process from the complex case to obtain my bounds for the real case. And here's a happy cat. And that concludes my presentation. Thank you.
All right, let's all smash that reaction button and thank the speaker.